Hey guys, this is Mr. Fernando, and I'm here to go over all of the day one questions. Just straight up, if you want to pause here, if you want to write these down, or again, come back at the beginning of the video each time I do a problem. I'll be referencing these equations. I'm probably not going to write them down every single time, but I will be working through each problem. So this is day one. Tomorrow we'll have day two video of just the review, me going through each question. And we're going to start off with the first ones, which are going to be about geometric sequences and arithmetic sequences. So you guys can focus in on thinking about these two equations. A1 times the rate, n terms, so like the term that you want to know, minus 1. Or for an arithmetic sequence, it's A1, the first number, plus the term you want, minus 1, times the difference, or what's being added or subtracted each time. So let's go to question number 1 and 2. So I'm going to go ahead and actually do, I think, number 3 and 4 first. That way you can kind of see the equation like with an actual problem. Then maybe these ones will be a little less confusing, because I think the first two, because it is you don't know what term you want, might be a little more confusing. So for a geometric sequence, right? I'm doing a geometric sequence, and I want to know the A46, or the 46th term. So I'm going to start off by writing A46 is equal to, almost all of these equations start with, what's the beginning number? What's the first number in the sequence, in which case this is -2. From here, you have to notice what's the rate, right? What's happening each time. And then from here, right, if I continue going, right, it's going to be multiplying each time by -2. So what's happening from -2 to 4? -2. 4 times -2 is -8. -8 times -2 is 16. So the next part of my formula is first number times my rate, which is -2. And then from here, you do the term you want minus 1. So in this case, 46 minus 1 is 45. The reason why this works, right, is if I'm on step 1 and I want to know what's number 40, the 46th number in the sequence, right, that would be 45 steps ahead of the very first number. Like, you're starting on the very first number already. So it's not 46 ahead of you, it's 45. So if I now do up here, right, what's the equation for the nth term, right? So you don't know what term yet, right? It would be the base formula would be an, n being the nth term we don't know. Very first number, 432, times, in this case it's a little tricky, right? What's being divided each time? Well, this time it's divided by 6 every single time. So multiplying, right, that'd be like saying times 1/6, or same thing as saying divided by 6, because again, you're dividing by 6 or you're multiplying by 1/6. And in this case, right, instead of a number that we know, we would just write n minus 1, the term that you'd want minus 1. For this one, we could execute. It's a really, really long number. Like if I did this one, -2 times, let's see, parenthesis, -2 to the power of 45. Yeah, it's giving me something that looks like this, 7.036 to the power of 30. It's give you a really large number. So for today, we'll just take this. If you got this down, it showed me that you understand it. For the arithmetic sequences, it's very similarly, right? What we're seeing here is what is being added every single time, because what arithmetic versus geometric is what's multiplying each time. Arithmetic is what's being added every single time. So on this one, I noticed that I'm adding 30 each time, and that's going to be important because it's a part of our equation. So I'm going to do number 4 first, and then do number 2. Our formula, I want to know what the 42nd term is. So A42 is equal to, what's my very first number? 22. And then it's, because, like, think about it, it's being added each time. I want you to think that you're adding, just like how in arithmetic, you're adding the next couple steps. So I'm starting at 22. I want to know what the 42nd number is. So that's 41 steps ahead. So you would do 42 minus 1 to give you 41 times 30, right? The reason why this works is because you're taking, each step you take, you're doing 30, right? And we're doing that 41 times, because you're starting on the very first number, and you are doing 41 steps of 30 each time. That's why it's 30 times 41. And then this would be your answer. Obviously, this one you could actually solve, and it would give you an okay number, 41 times 30, plus 22. This one would be 1252. Or again, for right now, we're fine with just giving the actual sequence formula. So again, what would this be? Well, the equation would be a to the nth. We don't know what that is. Very first number is 6 plus n minus 1, or again, how many steps forward would you end up taking? And it's times, in this case, what's being added every single time. It is 13. It is 13 every single time. So that's the baby formula, actual formula. Okay, now we're doing some growth and decay. So we're talking about some growth or decay. These ones are actually both growth. I know this because it says increases by a certain percentage. This one's saying it's growing by a certain percentage every single time. So on both of these, we're using the growth formula. I'll write this one down of growth formula being, let's see, it is the very first number times your rate to the nth power, right? And in this case, in this question, we don't actually know what that is. So in this case, right, the rate, because we're talking about growing, right, our rate is actually something that looks like this. It is 100% plus our growth. So our formula for this one is going to be a to the nth, or I think it's actually t, my bad, is equal to our very first. She is at 8 endorsements, right? So Serena Williams, being a popular athlete, consistently receives new endorsement deals. Her agent states that the number of endorsement deals increased by 82% every year. If she currently has 8 endorsements, write an exponential growth equation, right? So she's currently at 8, and she is growing by 82%. So 8 times a growth of 100% plus 82% to the nth power of, like, we don't know how many years, right? So the final answer for this would end up being, I think it's actually, do we write it with y? I think we do actually. Exponential growth is gonna be y. So I'm gonna write y here. Y, or our exponential growth, is 8 times 1.82 to the t, or like, we don't know how many years, right? You could put 5 years and that would be a growth of 100 or 82% growth over a certain amount of years, times 8 being the beginning point. For this one, Ava and Trace start an online Instagram account that has 15,400 views so far. In addition, that number continues to grow 22% every week. How many views will they have after 4 weeks? So this time you're actually given how much time is passing, right? So in this case, right, we are starting with y is equal to starting point. This is how many views they currently have. The growth, right, is that it's growing by 22%. So like that would be 1 plus 22%, or 100% of the number plus a growth of 22%. So that would be 1.22. And then we do actually know it's after 4 weeks, because this growth happens every week. So it's exponentially to the power of 4. So 1.22 to the power of 4 times 15,400. That would give me total views of 34,116. And because this is views, my bad. Oh, not round to the nearest hundredth, actually. We were given that. Round to the nearest hundredth, this would be 0.15 views. I don't know how you get 0.15 views, but it says round to the nearest hundredth. Alrighty, next problems. Now we're actually going to looking at tables, right? Is it a linear or exponential function? Well, again, I'm looking basically right at my y's, right? This looks more complicated than what it really is. I want you to think about arithmetic versus geometric sequences, right? The idea here being that you're looking at your outputs are your numbers adding every single time? Like adding something every single time, or are they being multiplied by something every single time? So what do I mean by that? Well, going from -2 to 0, 0 to 2, 2 to 4, right? What is happening each time? In this case, right, it looks like it could be multiplying, but you can't. There's no such thing as a number that going from -2 to 0, 0 to 2, you can't multiply. You're adding. Each time, what's happening is +2, +2, +2, +2, over and over and over again, meaning it would be linear because it's adding by 2 every single time. So when it says for full points, how do you know? It's adding by 2 every single time. This one, is it linear or exponential? Well, looking at these numbers might be a little confusing, but you might get clued in by these last 3 especially. You're multiplying by 4. It's multiplying by 4 every single time. So this one is exponential. This one's exponential because it's multiplying each time. It's an exponential function because really think about what happens. So 4 times 4, 16. 16 times 4, 64. And so on and so on and so on. That curve is about to explode because it's exponentially growing by times 4. All right, now let's start evaluating, right? This one starts to use a lot of our exponent rules. Well, all I'm doing is I'm putting this -1 right here. So I'm gonna write f of -1 is equal to 3 times 2 to the -1st power. So what ends up happening here? This right here, I think it's a lot of people. Anything that's to a negative exponent, think to your rules, right? It's applied everywhere. This ends up becoming, looking like this. It flips. It's becoming 1/2 to the power of 1, or just 1/2. And we still have the times 3. So our answer would be 3 times 1/2 would give me 3/2, or 1.5 is your final answer. So again, really think about what that negative exponent does. On this one, again, that 5 is just going to be placed right there, and then you execute. So in this case, what? I have 0.75 to the power of 5 times 3 ends up giving me 0.71, and I'm just going to round to the nearest hundredth. Yeah, that should be good. It's 0.071. If you want to keep going, you could go 1914063. Because again, all I'm doing, 0.75 to the power of 5 times 3. All right, exponential growth and decay, identifying what it is. So from here, just to give an idea of the formula, right? We are looking at either a growth or a decay. And when you think about your growth and decay formulas, right? I'm going to scroll down to it. Look at your growth and decay right here. You are either, for a growth, doing 1 plus something to get your growth over 100%, or you're doing 1 minus something, meaning like it's going under 100%. It's a decay. You're going down in value. So in this case, right, if I'm looking at these 2 numbers that I just underlined, I can see that this one, it must have been 1 plus something to get to 1.02, right? Like there's no way I've subtracted anything. So this one's a growth. This one's a growth because I know it's over 100%, and I end up adding 0.02. In this case, right, that would be 0.02. What is that as a percent? My rate is a growth of 2%. What about decay? Or sorry, I just previewed it. So this one, again, I must have done 1 minus something to get to 0.87, right? So in this case, what did I subtract? I subtracted 13. 0.13. In this case, right, you get 87%, or clearly I had took this, or a decay of 13%. Decay, growth. And you know this, right? Because it's over 100%, under 100%. Alrighty, man, we're going through these tables. So I'm going to go ahead and fill these out. -1, 0, 1, 2, 3. These will be filled out. Apologies if yours currently isn't. On the test and review day 2, we'll make sure to do this. So basically, it is just executing and then yeah, executing and then graphing it, right? So let's look at this one. -2, I'm going to be inputting right here, right? So if I did this one, as a reminder of what negative exponents do, 3 times 2 to the -2nd power, negative exponents, that makes it flip, right? That makes it do and look like this. That's the same thing. What I wrote is the exact same thing. 2 to the -2nd power is the same as writing 1 over 2 to the 2nd power. Sorry, yeah. So in this case, right, this would end up becoming 3 times 1 over 4, or 3/4. So that's going to end up being 0.75. Alrighty, let's do the next one. Again, I'm going to kind of go through fast on these ones, right? Same next one would be 3 times 2 to the -1st power. It does that flip, right? So what this ends up becoming is 1 over 2 to the 1st power, but I'm not going to write that. 3 times 1/2 would give me 3 over 2, which is 1.5. 3 over 2 is 1.5. Let's start thinking of what our rules tell us. Anything to the power of 0, so if I put a 0 right here, is 1. Every single number. So 2 to the power of 0 is 1. 1 times 3 would be 3. Now here comes like a little trick, right? I will still keep going, but you should be able to maybe notice what's the pattern. I'm multiplying by 2 every single time. Think about like how it's an exponential function, right? So it has to have a pattern. So 1.5 times 2 is 3. 3 times 2 would end up giving me 6. 6 times 2 is going to end up giving me 12. 12 times 2 is going to be 24. Well, let's see if that actually ends up being true, right? So if I had 1, 3 times 2 to the power of 1 would end up being 3 times 2, which is 6. For the next one, if I put this 2 right here, 2 to the power of 2 is 4. 4 times 3 is 12. Oh my goodness, look at that pattern, how it's going to be consistent. And now let's graph it. I'm pretty bad at doing this, so don't be too judgy. So right here, I'm going to say that this is -2. That's my x -2. And I'm going, again, I need to put a little dot there. It's 0.75, the best that I can do, right? Because it's x -2 up 0.75. Next one is -1, and I'm now up 1.5. Now I'm at 0, and then I'm at 3. And then 1 is going to be at 6. So notice how this curve is about to go crazy. At 2, I'm at 12. And then at 3, I'm at 24, which would be right here. And if I connect my dots, that's my exponential growth. All right, so for this one, oh my goodness, starting with a fraction, right? Scary. So over here, I've got 6 times 1/3 to the power of x, right? Well, I'm going to replace that with a -2. I'm going to input it. So I have -2 right here. Let's remind us what our negative exponents do, right? It makes it become a reciprocal. So it's 6 times 3 to the 2nd power. Because again, literally that's the same thing. It's just knowing your negative exponent rules. From this point, 3 times 3 is 9. 9 times 6 is 54. Now going for -1. So again, 6 times 1/3 to the -1st power. That's like saying 6 times 3 to the 1st power. 6 times 3 is going to give me 18. And then from here, anything to the power of 0 is 1. So I know that 1/3 to the power of 0 is going to be 1. 6 times 1 is 6. All right, let's see what keeps going from here. So I'm going to put in the power of 1. So right here I have 6 times 1/3 to the power of 1, which would be 6 times 1/3, or 6 over 3. So 6 divided by 3, that ended up giving me 2. and so you guys can actually start to kind of notice what the pattern here is as well. Same as I did over here, dividing by 3 every single time. So in this case, I could just do 2 divided by 3, write the answer, that answer divided by 3, and keep going. But I'll, for all intents and purposes, continue to do this, right? The next one, right, is going to end up being 6 times 1/3 to the power of 2. So in this case, this would be like saying 6 times 1/3 times 1/3, in which case this is 6 over, 6 times this, which would be 9. 6 divided by 9, right? If you did that, would give you decimal repeating 6. And just to confirm that, 2 divided by 3 would have also given me that repeating 6. And then again, just knowing what you're allowed to do, divide the next one by 3, and that'd give you repeating 2. Or you do the same thing, inputting 3 as your exponent. All right, let's try to graph this one, see if I can't mess it up. All right, negative 2x goes all the way off the map. You're at 54. Now we're at negative 1, and it's going to be at 18. Then we have 0x, in which case that's going to be 6, so that's right here. At 1, I'm at the number 2. At 2x, or x being 2, you're at 0.6, so like roughly right there. And then 3 is right there. So there's my exponential decay. Alrighty, final two questions. So on this one, we're talking about compound interest. So Maddie invests $2,658 in a retirement account after her basketball career is over, with a fixed annual interest rate of 9% compounded every year. What will be her account balance after 15 years? It's actually more of like a simple, because it's just compounding every year. So this one's actually very simple, of 2,658 times, I'm gonna make more space, I did that really large. 2,658 times, what's gonna be my interest rate growth here? It's 100% of this plus my interest rate. And we typically divide that annual interest rate by how many times it's being compounded. Like, right, in class we've been showing 1 plus 0.09 being divided by something. So if it was compounded daily, you divide by 365. If it's divided, or if it's compounding monthly, you divide by 12. It's compounding every year just once. So it's being divided by 1, and it's to the power of 15. So in this case, 2,658 times 1.09 to the power of 15. So in this case, this would just be 1.09, oopsies, 09 to the power of 15 times 2,658 would give me $9,681.72. All right, the next one. So this one is a true compound interest. It is compounding every month. So Bennett is starting with 6,154. And what's happening, right, is it's compounding every month at a rate of 8%. So that's 100% of the initial investment plus 0.08 being divided by 12. So in this case, right, it's being divided by 12 because it's a compounded every month. That annual interest rate is split up into 12 different months. And then the next question actually is, what's my exponent going to be, right? It's compounded every month, so I want to put how many months that's going to be. Well, right, if you think about it, 10 years times 12 months give you, I don't know why I had to do that, 120. It seems like a really big exponent, and it is, right? Because after 10 years, that's 120 months in those 10 years. So I have 6,154 times 1 point. Actually, I didn't even do this. What is 0.08 divided by 12 is going to be 1.08 0.066 exponentially. Oh, not exponentially, just repeating. So if you add 1 to that, and you do to the power of 120 times 6154, you'd end up getting 13,659 and 67 cents. Should have put some dollar signs on this. Compound interest rate, years, monthly, looking good. That is review day 1. Hope you scrubbed around. Thanks for watching.